So yeah, I'll probably have this posted up at YouTube later. All right, so this is I wanted to start this discussion talking about basic transformers. Because when we get to the pre-unit system, I'm probably going to spend a little bit of time on transformers because I want you to get this. But you also have to have experience with it. Okay? So the next trip, the next homework, there should be a homework out there, right? Okay. All right. So basic transformers. Your Boylston book also, if you still have your Boylston book, has a very good chapter on this, okay? But a basic transformer consists of two windings. And the most common way to show it, even though most transformers are not built this way, is like what we did with cores in machinery and controls. So what happens here with a transformer is we have coil number 1 has n number of turns. And then normally this is called the primary. Coil number 2 has number of turns N2. Okay? Now, bottom line is what we need to know here. So they look like inductors, and the natural response usually from your viewpoint is to look at everything that's a coil of wire as an inductor. Okay? So it has inductance, but one of the things that we do not study well here we do it with inductance, but what happens, I don't know if you guys have ever really thought about this, but really what an inductor is there's an induced voltage. It's called in motors we call it a counter EMF. But in an inductor, usually most inductors, the inductance is real low, so the voltage that's induced in the inductor is relatively small, okay? But it's also proportional to the current, okay? So, but what we do is we call this X sub L, the current equal to the voltage divided by the inductive reactance, okay? That's usually how we talk about inductors in AC circuits. But what that inductance really is, and what that reactance really is it represents the voltage drop in the inductor. Okay? Well, that's what's happening here. Only here, the voltage drop, there's a counter EMF. So there's what we call leakage reactance in these coils of wire, which we'll talk about later. But more importantly, what happens is there's a voltage that's induced. What happens is we apply an E1. And remember now, AC circuits, what's the difference between this capital E and little strict E? Justin, you know the answer? No?
Is capital E the source voltage?
They're both source voltages.
They're both source.
So what's the difference between making it a capital E and a strict E? Thank you. Which one's which? Yeah. This tells us DC. This tells us AC. Okay? So it really is, And for us, it's nothing fancy. It means AC means it's time varying, but in the power world, it means it's a sine wave. Okay? So, we have an applied E1, and what happens with a transformer is the magnetic flux links the two windings through the core, and we end up with an E2. A voltage generated. So E1 is the applied voltage to coil 1 of N1 turns, and E2 is an induced voltage in N2, in coil 2. And what ends up happening is, some things to remember. The voltage ratio is equal to the turns ratio. So the voltage that gets induced in E2 is proportional to the difference in, is proportional to the ratio of the turns. Most of the time we don't know the turns. So most practical transformers, all we're really interested in is the voltage ratio. So if we know the voltage ratio, we know the turns ratio. But most of the time in practical applications, we do not go calculate the number of turns. Okay? Okay. So, what that means then is E1 over E2 is equal to N1 over N2. So if N1 is 200 turns, and N2 is 50 turns, what's the turns ratio? Or 4 to 1, right? Okay. What's the voltage ratio? Thank you. Very good. 4 to 1. So, if I put 480 volts into E1, what's E2 going to be? I don't know, is it?
Over into is 4, and then you multiply E2 together next time, and then you divide 4.
So what's E2?
E2 should be 120.
That's right, it's 120 volts. Okay? And this is a very common transformer because 480 is a very common distribution voltage. And we need 120 volts for receptacles. So that's the case. Wherever we have a receptacle, that receptacle's got to be connected to a transformer somewhere that's rated for 120 volts. Does that make sense? So from this day forward to the day you're in your grave, whenever you see a 120 volt receptacle, you should think, Harstein told me that thing is connected to a transformer. Okay? And it is somewhere. Okay? Alright, now, what if we worked it backwards? What do you think E1 is going to be? That's right. For all intents and purposes, all of our transformers we can run backwards. Okay? If you get into the utility world or the power world and work with these things a lot, you'll get used to the instances where you can't. Okay? Okay? Okay. Now, We normally then abbreviate a transformer as just 2 coils. All of our transformers are going to be iron core. If you look at ANSI symbols, they usually have 2 lines in there. They usually include 2 lines in here to indicate iron core. I just put the 2 lines in there because everything I do is iron core. Okay? But this is going to be the same thing. N1 equal to 400, or was it 200? 200. N2 equal to 50. If I apply 480, I'm going to get 120. Also, transformers use a dot convention, or they'll use an H1, H2, they'll use an X, an H and X designation. Okay? So, the dot, or I'll call it HX convention. What does that mean? It really has to do with the phase shift. Okay, if you can get used to this, practically speaking, there's no phase shift across the transformer. So if I make these phasers now, and by the way, these are RMS values that I'm using. Okay? E2 is going to be 120 angle 0 degrees. So E1 is going to be my reference, the one at 0 degrees. And what happens is, that transformer, what that means is, when H1 is the, I'm going to call it, same phase as X1. Okay? Because you can change the polarity of that secondary winding by, when you assemble it, flip it over, or winding it the opposite direction. So we can take that same transformer, and we're not going to make a big deal of this in this class. I just want you aware of the notion that the numbering H's and X's indicate polarity. And in the AC circuits world, that means it indicates the phase. Okay? If I was going to use the dot convention, I'd put a dot there and a dot there. The other thing that implies, and maybe this is a little bit easier to comprehend, once we hook a load up, we're going to end up with an I1. If I have current flow into the dot or into H1, current flow is going to be out of X1 or out of the dot. Up here, I1 into X1, I2 out of X1. Did I say that right? I1 current flow into H1 and I2 current flow out of X1. Okay? Okie doke? Alright, now let's hook a load up. And readings. So, and readings. Okay, now, what does that mean? All right, first of all, let's hook up a load. So let's take our transformer, and it's going to be 4-to-1 rating, turns ratio. So I'm going to get 120 angle 0 out. And now I put a load on here, and let's just say that it's 0.5 and J 0.3. Now then, we have a current flow then that results in the secondary, I2. How do we get that current? Well, we have 120 volts. This is the same as looking at this as a series circuit. Where we have 120 angle 0 degrees. Across a 0.5 plus J 0.3 ohm inductive reactance. So how much current is going to flow? It's going to be E2 over Z, and I'm going to call this Z to load. So 120 angle 0 degrees over 0.5 plus J 0.3. What do we get?
We got 205.8 and angle of negative 30.
Okay. Okay, very good. Now, what about I1? How do we get that? Well, transformers, practical transformers, are lossless. What does that mean? P-in equal to P-out. Okay? Now, the way I remember, there's a couple of transformer equations that you want to remember. Even though you don't remember this much, or use this much, the way to remember it is the voltage ratio is equal to the turns ratio. Okay? The other thing to remember is, in the AC circuits world, with transformers, if they're lossless units, lossless transformers, this translates to S in equal to S out. But I write VA, apparent power, as volts times current. So what I say is that V1, I1 equal to V2, I2. Okay? Don't ever forget that formula right there. So that means I know V1, this is V1, and I know I called it E1 earlier. I have a tendency to do that. I interchange V's and E's quite a bit. Okay? And then 120 is V2. So I know V1, V2, and I know I2. Now I calculate I1. So I1 is equal to V2 over V1 times I2. But I know V2 over V1, don't I? The voltage ratio? What is it?
V2 is 1. Yeah, V2 is 1, V1 is 4, so it's 4 multiplied by I2.
So the turns ratio is 4, but in this case, it's 1 over the turns ratio. Yep. So this would be 1/4 of I2. Or you could put in here 120, and in this case, you can put the angles in if you want. Angle, they're both at 0, times I2, 205. And so what do we get for I1? same phase angle, right? So for us, ideal transformers, we don't lose phase shift. Plus an ideal transformer. Okay? What time we got here? Okay, good. Okay, now, next question is what is the VA? Being transformed. Well, it's V1 times I1 or V2 times I2. They're the same. Let's do V1 I1. .480 angle 0 degrees times 51.45 angle negative 31 degrees. If I want to call it VA, if I want this to be S, then I have to conjugate that. So what do you get?
Yeah, I got 24,695.8. And angle positive 31.
Okay? And if we wanted P and Q, we just put that in rectangular form to give us P and Q. Which would be the same as I squared times I2 squared times 0.5 or I2 squared times 0.3 for Q. Okay? Because our transformer doesn't lose any VA or watts. Okay? Okay, now, ratings. When in the problems I tell you that a transformer has a particular rating, I may tell you in this example, that this transformer is rated for 30 kVA. Okay? What I'm doing is I'm telling you the maximum VA that can go through that transformer. Does that make sense? Okay? So when I ask you then for rated currents, one of the things I think students have a lot of problems with, that's why I'm exaggerating this, is the difference between the actual current flow and what the rated current is. What we just calculated was the actual current flow. We actually put a load on there of 0.5 plus J.3 ohms, okay? And then we calculated the actual current in the secondary and the actual current in the primary. If I told you that the transformer was rated for 30 kVA, then I would ask you, what is the rated secondary current. And what that means is, what is the maximum current that you could push through this transformer now? So what you do is you use the rated VA, and on the secondary divide by 120, so I2 would be S rated over V rated. And I'm not interested in phase angles at this point. I'm only interested in maximum, so I'm just going to put them, I'm going to just use magnitudes. So this would be 30 kVA over 120. So I2 rated is what?
250 amperes.
50?
250.
250. What was the actual? 205, right? So we're not overloading the transformer. When you draw more than 250 amps, if this is a 30 kVA transformer, you're overloading the transformer. And it'll heat up more than it's designed to heat up. Okay? What's I1 rated? Well, there's two ways you could get this. We know the transformer is a 4-to-1 ratio, so we could just divide by 4, or we could multiply it by the voltage ratio. Or we could also use the primary ratings. The VA rating is the same for both the secondary and the primary. Okay? So now, for the primary, this would be S rated divided by, this should have been V1 rated. This is going to be V2 rated. No, I did that wrong. This should be V2. This is V1. Okay. So, 30 kVA over 480. Volts. And what do we get for I1 rated? What is it? Okay. Now, if you take a look at the homework, homework number 3, that's what's going on here. So all these transformers, there's lots of examples. There's like 10 examples here for you. I guess there's not. Well, I better make sure there's not 2 pages to that. Okay. All right. That fundamental discussion we just had on transformers is the foundation for everything else we're going to do, including 3-phase transformers. With 3-phase transformers, then we really need to rely upon the fact that 3-phase is just 3 single phases connected delta or Y. Okay? So, okay. I think that's probably a pretty good place to quit for today. Do we have any questions?
Yeah, I have one question.
Yeah.
It's about Thursday. Well, on the schedule it says that we have a Orville tour, like, how's that gonna work out?
Oh, this Thursday?
Yeah.
Yeah, no, I didn't get an order. I didn't get the schedule.
Okay.
I didn't get that scheduled yet. So, I'll go, when we break up, I'll send my contact there an email, see if we can get that scheduled. Sound good? Speaking of that, let me go ahead and, I'm gonna go ahead and stop this.